All right, let's talk about single replacement reactions. They occur when an element replaces an element from a compound to form a new substance. So the element that's by itself substitutes in for one of the elements in the compound to form a different compound, and then the element that got displaced will be a free element. Whether that reaction will occur or not is based on something called the activity series, which we'll go in a minute. And that means all these reactions won't go. It has to be active enough to cause the displacement. Elements at the top of the activity series are the most active and will displace anything below them. The reverse reaction won't occur though. So we could have sort of a formula: A plus BC goes to BA plus C, where the A is replacing the anion of a salt, for example, or A plus BC goes to AC plus B, which is the bigger category where a metal atom will replace another metal atom in an ionic compound, or hydrogen. Here are some basic kinds of them. Group 1A metals react vigorously with water to form hydrogen gas, and then a hydroxide of the metal. Group 2A metals will react with water, but not as vigorously. So your overall would be the metal plus water goes to a metal hydroxide and hydrogen gas. But it has to be active enough. Things that aren't active enough won't do that. A metal can react with a non-oxidizing acid like hydrochloric or acetic, and also liberate hydrogen gas. Metal plus non-oxidizing acid like HCl or acetic acid would produce a salt and hydrogen gas. Now the metal doesn't have to be quite as active to displace hydrogen gas in this particular case. But in this case, the metal is replacing a hydrogen atom, both those. Now metals can replace other metals. You can take a salt plus a metal, goes to a second salt and another metal. Our idea of putting copper into silver nitrate from our original example at the beginning of this chapter, you can go back and watch that video. The copper will displace the silver because it's more active, and so you get silver by itself and copper's in solution with the nitrate. The reverse doesn't occur. If I took silver metal and put it in solution containing copper 2 ions, I get a big fat no reaction. And so that's how the activity series will work. And if you see a reaction like that one, it is proper to write NR or write the words no reaction, because that reaction does not take place, at least not by itself. Halogens tend to form anions in ionic compounds, and they will undergo single replacement reactions with each other. These reactions will work the same way, except you're replacing the nonmetal of the ionic compound. The activity series is essentially group 7A on the periodic table. Fluorine's at the top of the column and therefore most active, and it will go down to iodine being the least active of the commonly encountered halogens. And for example, diatomic halogen plus a salt goes to a second salt and another diatomic halogen. So I take fluorine, react to put it in a solution with sodium chloride, I'll get sodium fluoride and chlorine gas. We wouldn't really do that in lab because both those gases are pretty toxic. Usually, if you see a lab reaction with this, it's with bromine and iodine. But if I reverse that and say sodium fluoride aqueous and a bubble and some chlorine gas, I'm going to get a big fat no reaction. So what we're going to do then is we're going to look at these single replacement reactions. All of these will occur according to the activity series. We just need to figure out the products, and then we'll talk about whether or not they will occur. So let's finish these single replacement reactions. If I got the sodium plus the water, remember that displaced hydrogen gas, and I formed a metal oxide, which is sodium hydroxide. So that's our metal hydroxide that's formed. +1 hydroxides -1, so that's okay. You have to consider water solubilities of each of these salts. That's a soluble salt, it's a strong base, so that's aqueous. And then we'll liberate hydrogen in the gas phase. And then you just have to balance it. So we got H2 plus H. That's not going to even out, so we're going to stick a 2 there to balance out the hydrogens. And then we're going to put a 2 there, because then that'll balance out the hydrogens now that I've got rid of the odd one. And then because I put a 2 there, I'll need to stick a 2 there. And there's a balanced reaction. So that's an alkali metal reacting with water. Here's a metal, active metal reacting with hydrochloric acid. So we're going to get zinc with the chlorine, Zn and Cl. Let's consider the charges. That's a halogen, -1. Zinc is a transition metal, but when it forms an ionic compound, remember we said it forms a +2. So it's ZnCl2. Chlorides are usually soluble. That's not an exception, so aqueous. And we're going to liberate hydrogen gas. To balance the hydrogen to chlorine, I'm going to need a 2 there. Now these two are going to swap metals, so you're going to get Cu metal by itself plus SnNO3, and we'll say it forms a 10-2 instead of a 10-4, which it does. Now, here's the halogen replacement last but not least. So the bromine is going to replace the iodine instead of replacing the cation like it did in every other case. So we're going to end up with sodium with bromine. Sodium's +1, bromine's -1. So that's a good formula, and it's water soluble because it's an alkali metal there. Plus iodine, and likely that's going to be aqueous because I'm talking about a water solution. So it's going to be, but it's going to be I2 because remember your halogens are all diatomic. So to balance the halogens, I'm going to need to stick a 2 there and a 2 there to balance it all. So those are some examples of some single replacements. All right, let's talk about the activity series now, since that is what you're going to use to determine whether a single replacement reaction occurs or not. You're going to need to be able to refer to this. For purposes of our test, we'll give you the activity series without the cool color coding and labeling, but you'll have the ordering if you remember how to use it. Lithium is the most active. Moving on down, everything is less active than that. A lot of these active metals will displace hydrogen from water, steam, and acid. These in this next section, starting with magnesium, will displace it from steam. That is, the water has to get really hot, or acid, but not water. And then those in sort of that yellowish color will displace hydrogen gas from an acid only. Notice that's only slightly more active than hydrogen. So anything above hydrogen on the activity series will displace hydrogen gas from an acid. Everything below that, and that sort of pinkish color, I guess, has lower activity and therefore will not displace hydrogen gas from an acid. And that's how the activity series works. Anything above it will displace anything below it. So let's consider whether or not these single displacement reactions will or will not occur. So if we got magnesium solid reacting with water, now if we assume that that's room temperature water and not hot water, magnesium wasn't active enough to displace it from room temperature water. It was in that second group. The water had to be really hot, or maybe superheated steam or water vapor at a very high temperature. So not so much. Now, if you look at nickel, nickel was above hydrogen on that activity series we just looked at, so it will displace hydrogen gas from the acetic acid. Gold versus lead. Now, gold, you can still see the bottom of the activity series there. It's at the very bottom. Gold is very difficult to oxidize, so much so you still see it on the bottom of the seafloor from when some of those Spanish ships crashed in a hurricane or something. And so it's very notoriously difficult to oxidize. And so that reaction will not occur as written. Iodine trying to displace chlorine. Iodine is below chlorine in the column, therefore it's less active, and so that reaction will not occur as written either. And so then we'll move on to double displacements in the next video.